Hello students. നമ്മൾ കഴിഞ്ഞ ക്ലാസ്സിൽ ലഗ്രാഞ്ചിയൻ ഫോർമുലേഷൻ ഉപയോഗിച്ചുകൊണ്ട് സിമ്പിൾ പെൻഡുലത്തിൻ്റെ ടൈം പീരീഡും ഫ്രീക്വൻസിയും ഡിറൈവ് ചെയ്തിരുന്നു. ആ സമയത്ത് നമ്മൾ പൊട്ടൻഷ്യൽ എനർജി കാൽക്കുലേറ്റ് ചെയ്തപ്പോൾ സീറോ ഓഫ് ദ പൊട്ടൻഷ്യൽ എനർജി, അതായത് റെഫറൻസ് ലെവൽ ഓഫ് പൊട്ടൻഷ്യൽ എനർജി ബോബിൻ്റെ ഇക്വിലിബ്രിയം പൊസിഷനിൽ അല്ലെങ്കിൽ മീൻ പൊസിഷനിലാണ് ഫിക്സ് ചെയ്തിരുന്നത്. ഓക്കെ, അങ്ങനെ ചെയ്തപ്പോൾ നമുക്ക് സിസ്റ്റത്തിൻ്റെ ഒരു ലഗ്രാഞ്ചിയൻ കിട്ടി. നിങ്ങൾ ആ ലഗ്രാഞ്ചിയൻ ഓർമ്മയുണ്ടാവുമെന്ന് കരുതുന്നു. സോ ഐ വിൽ റൈറ്റ് ദാറ്റ് ലഗ്രാഞ്ചിയൻ ഫോർ യു again. So we obtained Lagrangian L of the system as half m L square theta dot square. You can easily remember because L equal to T minus V, so it will be the difference between kinetic and potential energy of the system. So this is nothing but half mv square, where v equal to L omega, okay, minus mgl plus mgl cos theta. This was the Lagrangian that we obtained by choosing V equal to 0, potential energy is equal to 0 at the mean position. Okay, now in several mechanical problems we will have to suitably fix the reference level while calculating the potential energy. And by practice you will understand that fixing the zero of the potential energy or the reference level of the potential energy is actually a matter of convenience, because as already we have mentioned, it's not the potential energy which matters for the system, but the difference in potential energy between any two given positions that the system is having. So let me make it clear. Let me consider two positions, two reference positions. Let me call this is position A and this is position B, and let them be separated by, say, a height h. Let's consider these two be two different positions in the gravitational field separated by a height h. Okay, now let's assume that we have a mass m which is at the level A initially, and I'm taking the mass m from level A to level B. So I'm shifting the mass from A to B, right? You know that for this some work has to be done. So what will be the work done? So you can see that the work done, you know, the work is done against the gravitational force here, so that is causing a change in potential energy. So I can say the work done here will be equal to change in the potential energy. It can be the gravitational potential energy as in our case, or it can be some other potential energy, like in the case of electric field, it can be, or electrostatic field, it can be the the electrostatic potential energy, whatever it is for charged particles. So this is the concept. Work done is equal to change in potential energy, right? Now as I told you, it's the change in potential energy which matters. Let me make it clear. So we can say that if VA and VB, let me define something. VA and VB and potential energies. Okay, like we are fixing potentials, we are fixing potential energies also. So I can say that the difference between the potential energies here, that is VA minus, or I can say I have taken it from A to B, no? So better I can write VB minus VA, like the final potential energy minus initial potential energy. The potential energy is here you can see coordinate dependent, right? Because the height is different. So VB minus VA, that is equal to change in potential energy, you know, right? That is equal to work done. I can say this is equal to mgh. You know how it comes, mgh. this is nothing but force times displacement, and force is equal to mg, the gravitational force, times displacement. Displacement is equal to h. So force that we are exerting against gravitational force, okay, which will be equal in magnitude to mg. So the direction of force and the displacement can be taken as same, and so it becomes plus mgh. That's why now it's mgh. F dot s is equal to fs cos theta. So it will be equal to simply fs when theta equal to 0, right? That is the Vb minus Va is equal to mgh. So that is the just mathematical form of this equation, what I am calling as equation number 1. So let me call this one for the time being as equation number 2, right? Now see, if now we have two choices. We have two choices regarding the fixation of the reference level of potential energy. So for convenience, you can fix either level A as the reference level or level B as the reference level. Okay, so let me say, if I'm taking two cases separately, if level A is taken as, if level A is taken as the reference level, so we have the choices here with us, this up to us reference level. Then if A is taken as the reference level, then the meaning is that we will fix arbitrarily, we will fix the potential energy at A is equal to 0. That is meaning fixing the reference level. The potential energy of the system at the point A, or with respect to the point A or the level A, is fixed as 0. Okay, that is the meaning of taking level A as the reference level. Now if VA equal to 0, you know, equation 2 will give you that VB minus 0. So VB equal to what? mgh. VB equal to mgh. What does it mean? It means that if VA equal to 0, then the potential energy of the mass M kept at B will be equal to simply mgh. That's quite clear. Now the idea will be more clear if we do the reverse. What is that? If level B is fixed, if level B is fixed as the reference, so it's all a matter of convenience, as I told you. Then what do you have to do? We have to fix VB equal to 0. That is the meaning of fixing as a reference. VB equal to 0. When VB equal to 0, what does it mean? Equation number 2 will tell you that minus VA equal to mgh, right? 0 minus VA equal to mgh. Or what is it? It means that VA is equal to minus mgh. VA equal to minus mgh. So what I note is the sign of the potential energy. So you can see that from let me conclude, this is equation number 3, and this one let me call it as equation number 4. So you can see that the potential energy of the same system is either mgh here in my example, or it's minus mgh. So whether it is expressed as a positive quantity or a negative quantity will depend on solely on the choice of the reference level. Okay, and this choice is up to us. You can choose the reference level as per the convenience, and the only logic behind choosing the reference level is that it should result in simplification of the mathematics involved in the problem. So depending on the symmetry of the problem, or depending on your mathematical convenience, you can choose the reference level. It won't affect actually the final result of the problem as far as we are doing the Lagrangian method. I hope that it's clear to you. So whether or not the potential energy is positive or negative depends on the way in which you choose the reference level. So why I told you this one, because we had chosen the, let me come back to our simple pendulum problem, where we have fixed the zero of the potential energy at the mean position. Hope you remember that in our earlier solution of the simple pendulum, we had fixed V equal to 0 here, means that was our reference point. When V equal to 0 at C, okay, we took this one as height h, you can see here, the extreme position, right? This is a D is the extreme position in the diagram. So we took that the potential energy at D was taken as simply V equal to mgh, and we then calculated the Lagrangian. Now, as I told you here, what will be the Lagrangian of the same system if the reference level is not fixed at the mean position? Instead, let me shift to the reference level. Let me say that let V equal to 0 be fixed at the pivot point A. I'm fixing the reference level to be at the pivot point. Okay, so means the origin. Okay, I can take if the origin is taken as the pivot point, right? So let me take this is 0, right? Now if this is 0, then you can see that the coordinates are x and y here. The coordinates are x and y here. So automatically what you can do is that can do x plus x and y as what do you say in terms of the length L and cos theta. So you can see from figure, I'm just writing it here. So from figure, how do you write x? X is nothing but, can you write it as x means x coordinate, and y means just the y coordinate. So if this is the origin, you can take, so this one is the y coordinate, right? Because of this particular mass, this is the y, and this much is x, right? This is x because this is the origin. You can just consider. So x, I can write this one as what? L sine theta. Am I right? So x is equal to L sine theta, right? Now y, what will be y equal to? Y is equal to, see, y, I have fixed A as the origin, so y is taken vertically down. So I can say that y is equal to minus, I put it minus because it is downwards, okay, with reference to the reference level V equal to 0. So minus, I can say L cos theta, right? Minus L cos theta. So I have to find out the kinetic energy. So what will be the kinetic energy? So kinetic energy T is equal to half m v square, right? Half m v square. And you know that in terms of the Cartesian coordinates x and y, half m v square will be equal to simply half m, right? Half m x dot square, that is dx by dt, plus what? Y dot square. Am I right? Because v square will be equal to, is not? V square is equal to Vx square plus Vy square, and Vx equal to x dot and Vy is equal to y dot. So it is half m x dot square plus y dot square. Now can you substitute it here? So I'm substituting it here. It's equal to some half m into, what will be x dot square? So I have x here. So what will be x dot? I'm writing here itself. X dot will be equal to, what is that? It will be L cos theta, is not, into theta dot. L cos theta into theta dot. Just differentiate. Okay, function rule. So L cos theta into theta dot. And what will be y dot equal to? From this one you can write y dot. So what is y dot is equal to? So it will be cos theta is minus sin theta, then theta dot. So it will be plus. So it will be again L sin theta into theta dot. Okay, that will be the thing. So when substituting here, half m x dot square. X dot square will be L square theta dot square cos square theta, plus y dot square will be equal to L square sin square theta into theta dot square. So what will happen there? You know, L theta dot square becomes common there. Okay, you can do directly that one also. I'm just writing. So it will be equal to what will happen, that L square theta dot square will be common, and what remains there will be sin square theta plus cos square theta will be equal to 1, and you are getting simply this is equal to what? Half ml square theta dot square, and that was nothing but the same thing that we have got here, is not right, in the previous Lagrangian. So you can see that the choice of the origin, okay, or shifting the zero of the potential energy is not going to affect the expression for the kinetic energy here. Now let's see what will happen to the potential energy of the system. So let me calculate potential energy. So V is equal to, what is V equal to? V should be equal to minus, right? Because this is the position of the bob. D is the position of the bob, right? that we are considering, for which you have calculated the the kinetic energy. So D need not be the what you can say, it need not be the extreme position. It can be one position that is intermediate, where it is still moving. That is why we have taken V is equal to x dot square plus y dot square. If it is extreme position, automatically V will be equal to 0. So you are taking an intermediate position. So V is equal to, what I should write is that at that position, I can say it should be mg, okay, into this vertical height, right? Mg, it won't be mghy, it will be mgh only if the reference level V equal to 0 is chosen here. Now my reference level is here, so I have to take mg, that is the thing, into, instead of h I have to take the y component, the y coordinate. And what is the y? That is minus y, so it will be minus mgy, right? Minus mgy, that will be the thing, okay? Or I can say mgy, but this y is what? Minus, okay, right? You know why? Because I have to take it from the 0 point, from A to B, that is to be taken, because the reference is now A. So which is equal to minus mg, what is y is equal to? Okay, y is equal to L cos theta. You can do it in two ways. One is that either you can take minus mgy, or you can write mgy and then y equal to minus L cos theta, as we have done here. In whatever way you can take, okay? So this is the thing. So minus mgl cos theta, that is the thing we are getting. Now this is the kinetic energy. Let me say that this is A and this is B, right? So what will be the Lagrangian of the system using this reference? So that is nothing but T minus V. So what will be T minus V equal to half m L square theta dot square, that is the first term, minus, and this minus will become plus. So it will be plus mgl cos theta plus mgl cos theta. So this is the Lagrangian for the system with the zero of the potential energy fixed at the pivot point. Now look at the expressions that we have obtained right now and we obtained before. So you can see this was the first Lagrangian by fixing the zero of the potential energy at the mean position, and this is the Lagrangian by fixing the zero of the potential energy at the pivot. So can you see that they are not one and the same, right? So both are having two terms which are the same. So half ml square theta dot square plus mgl cos theta is here, and the same thing is here, but there is an additional term over here, right? Is it not? Okay, and the shifting of the reference level of the potential energy has resulted in some additional term, which is, you can see it's mgl, and L is a constant because it's an unstretchable string, so it's an additional term. So adding a constant to the Lagrangian, that is only result, and you know that adding this constant to the Lagrangian is not in any way going to affect the solution of Lagrange's equation of motion. You know why? Because the Lagrange's equation of motion, it takes into account some derivatives. Okay, what is that? One is dou L is taken with respect to what? Dou Qj dot. Here it is what? Dou theta dot. Okay, now, and the second one is what? Okay, the second one is dou by dou L, dou L by dou Qj. Dou L by dou Qj is what? Minus dou L by dou Qj is dou L by dou theta. Okay, that is equal to 0, right? So you can see that the Lagrange's equation involves the derivative of L with respect to theta dot and with respect to theta. So this mgl will not have any effect, because when you take the derivative of L, this constant term will be vanishing. Okay, so it will not make any impact on the final equations that we are going to get. It will not affect the time period or the frequency or whatever we need. Okay, so this is something that you have to keep in mind. So my conclusion, and this was what I wanted to tell you, that see, the Lagrangian of a system need not be unique. So that is your take home from the session. The Lagrangian of the system of a system need not be unique. Means you can have several Lagrangians for the same system, need not be unique. Depending on the choice of the coordinate system, depending on the choice of the reference level, same system can be represented by different Lagrangians. But once you substitute this Lagrangian in the Lagrange's equation of motion and solve for it, you will be getting the same physical results. Okay, and that is a wonder. So this is the idea that you have to keep. Later, when we discuss what is known as canonical transformations in a later module, I will just prove that the Lagrange of the system is not unique. Okay, and you will see that a system can be represented by L dash, another Lagrangian, where L dash can be connected to maybe an original Lagrangian. I cannot say original because both are representing the system. L plus some df by dt, where f is what is known as a generating function and all. Okay, we'll see that. I'll be proving this one later. Okay, so the Lagrangian of a system can differ from another Lagrangian at the most by the total derivative of a function. Okay, that we will prove later, but remember for the time being that this is a fact. Okay, the same system can be represented by different Lagrangians, but the physics of the problem will remain the same. Okay, so keep this idea in mind. It's not the potential energy which matters, it's always the change in potential energy or change in potential. I told you, or you know, that potential is nothing but potential energy per unit mass or unit charge. Okay, so that is why we have been discussing. Okay, I think I can connect it. Okay, I can connect it with what you call in your lab, okay, as the EMF of the cell and all, okay, right? When we discuss it, so you usually express that EMF equal to say that 2 volt, okay, for a cell. Now it means that if you fix the potential of the negative terminal as 0 volt, then potential of the positive terminal will be plus 2 volt. That's the meaning. And you have another freedom. You have the freedom. Okay, you can, if you want, if you like, you can fix the potential of the positive terminal as 0 volt. Then what would be the potential of the negative terminal? That is interestingly minus 2 volt. Okay, and this is exactly what happens when you are using dual power supply in your postgraduate practicals. You'll be using what is known as dual power supply. Hope you remember when we were doing your op-amp experiments, okay, to terminals 4 and 7, you are applying plus 15 volt and minus 15 volt. Okay, so hope you remember that one. Okay, so what you are doing is that you have got two cells. This is exactly what is happening. So 2 cells. Okay, you just consider that you have got 2 batteries instead of cells. Let me call it a battery, and this battery, okay, are connected end to end. They are connected end to end. Okay, so that positive, negative, positive, negative. I have 2 batteries. Okay, I'm just showing some pair of cells. So what is happening is that the EMF of this battery, I can say E1 is equal to say 15 volt. And EMF of the second battery E2 is also equal to 15 volt. Okay, so I have 2 similar batteries and I have just connected them end to end, and I will take 3 terminals from here. 3 terminals are taken from here. 1 is taken from the positive terminal, 1 is taken from the negative terminal of the combination, and 1 will be taken from the middle of the 2. See, this is what is happening. Now what we do is that we will fix that the potential of the middle, okay, potential of the middle terminal is taken as 0 volt. So that is what we are fixing, right? Potential of the middle terminal will be fixed as 0 volt. Now if the middle terminal has got 0 volt, then I can say the right terminal, what I have drawn here, which is connected to the negative, with respect to this 0, this is minus 15 volt. This is minus 15 volt. And with respect to the 0, the left side, which is a positive at higher potential, this one will be what? Plus 15 volt. And this is what we call as the dual power supply, DPS, where you have got, okay, plus 15, minus 15, and you call this one as ground, right? Is not? This is what you call as ground, and you connect it to the ground in op-amp. Okay, you connect 4 and 7, 4 to minus 15, and 7 to plus 15, and you also ground in some of the case. Inverting amplifiers, non-inverting amplifiers, you are using ground, and the ground is nothing but the 0 of the potential energy, and this is exactly what is happening. So here also the same concept you can see. It's the reference level which makes, okay, all the concepts like this. So just I try to connect it with the electric potential. It can be done with any kind of potentials. Okay, so hope that it was useful to you. This discussion we will be using these ideas maybe in some other problems as well. Okay, thank you.